All right, welcome to the screencast on hearing. I'm going to try and keep an eye on the time, and we might break this up into two screencasts so I'm not rushing. And really, they say that 10 minutes or less is best for videos because people space out after a few minutes of just watching video. So, sound. How do we want to understand sound? Sound is actually a mechanical sense. It is caused by disturbances in the air or pressure waves produced by a vibrating object. So, air passes over my vocal cords, they vibrate. Those vibrations then disturb the air and set up traveling waves in the air, and that is where sound comes from. Waves have a number of different properties. There are two of them we care about. We care about frequency and we care about amplitude. Wavelength, not so much, even though it's kind of tied in with frequency. Yeah. So if we look here, up top, this is frequency. If you assume that this red wave and this blue wave are moving at the same speed, which all sound does, the red peaks will all pass one point in any given time faster, or more red peaks will pass one given point in space at greater frequencies than the blue peaks. Right? So if you're just sitting there watching the peaks go by, more red ones will go by in the same period of time than the blue ones will go by. So that's frequency. That's how your brain determines pitch. High frequency, high pitch. Low frequency, low pitch. With volume, that is amplitude. So down here we have two different waves, the green waves with the lower amplitude, the blue waves with the higher amplitude. This almost inherently makes more sense. If you think of these waves as being water waves crashing on the beach, which have the same physical properties as sound waves, because air is technically a fluid like the ocean is, a larger wave, when it crashes on the beach, has more energy. It is going to make a louder sound than the shorter wave crashing on the beach. Now, the way this works with your ears is that the higher amplitude waves have more energy behind them, and they make a stronger, more powerful impact on your hearing structures when they hit them. So it's very much a physical sense. There are three parts to the ear. I will just read this over while you look at this picture right here. So you have the external or outer ear. In lecture, you do want to keep separation, I guess, between the earlobe and the external auditory canal. Just remember that there are two of them. But for the most part, I just consider all of this the outer ear, and its function is to channel sound waves into the middle ear. These structures right here are called the middle ear, and collectively they are responsible for transmitting the sound waves to the inner ear and also amplifying the sound waves, so increasing the amount of pressure that gets transmitted to the inner ear. And then this whole structure right here is your inner ear. This snail shell looking part of it is the cochlea. The cochlea is where vibrations become neurotransmitter release. That's where transduction takes place. So this is where the rubber meets the road. All the other structures of the inner ear, this stuff over here and this thing here, have to do with equilibrium. All right, so we are going to talk through the points on this slide right here while we look at another slide. The one I'm going to skip to, I have moved. It's actually 2 slides ahead in your version of the PowerPoints, but I wanted it next. So skip down to 1, look at that, and we're going to have sound collected by the outer ear. Then that sound is going to hit the tympanic membrane. The tympanic membrane vibrates when the sound waves hit it. It is hooked up to a ossicle, a bone called the malleus. The malleus is set in motion by the tympanic membrane. It then hits on or vibrates this next bone called the incus, which then vibrates this next bone called the stapes. So a lot of hearing is just one structure transmitting vibrations to another structure. So in this case, it's tympanic membrane, malleus, incus, stapes, and then there's a thin, flexible membrane behind the stapes called the oval window that opens up into your cochlea. So you have to remember that your cochlea is actually embedded in bone. It's part of your temporal bone. And there's a small opening in the bone that the cochlea is embedded in that allows vibrations into the fluid-filled chambers of the cochlea. As the vibrations are passing through the middle ear, they are being amplified. And if you come up here, there's two reasons why that happens. One is easy enough to understand. This is the leverage that you get from the ossicles. The other has to do with the size difference between the tympanic membrane and the oval window. So if you look here, these two at least are rather long bones, and they're having the force applied to one end. So they work like a lever and fulcrum, and you can, by moving the long end of a lever, generate a lot of force at the short end. So the leverage that the ossicles provide, or the mechanical advantage that the ossicles provide, increase the strength of the vibrations that are being transmitted towards the oval window. Then you also have to look at this size difference. Here you have your tympanic membrane, it's this big. Here you have your oval window, it's about the size of the base of the stapes, so it is much smaller. So I will just throw out a question. When is the last time you have checked the pressure in your tires? Because what we're talking about here is pressure waves. Maybe you have tires that are low profile tires, so you're supposed to be running 40 to 42 psi. What does the psi stand for? That's pounds per square inch. So pressure is measured in force per unit area. The area upon which the pressure is being applied is significant to how much pressure is being applied. So if you have a certain amount of pressure, let's say it's 10 pounds per square inch on the tympanic membrane, and all of that pressure gets applied to the oval window, but the oval window is only half the size, now the pressure is 20 pounds per square inch. So you're taking all of the pressure hitting a larger object, transferring it to a smaller object, and the pressure per unit area goes up. And actually, not only are you just transferring all of that pressure, you're increasing the amount of pressure. So the pressure felt by the oval window is much more magnified than the pressure that hits the tympanic membrane, because it's both the size difference and the leverage that is increasing the pressure. So then we get into the cochlea, which is this structure right here. And if you look at the way they've drawn it, it's one big tube here, or that outer tube, whoops, and then there is a smaller tube completely contained within inside of it. So it's actually got two chambers. And then you just need to remember that it's all rolled up so it looks like a snail shell or a cinnamon bun. I want to try and give you a better understanding of it. I haven't gotten a lot of feedback on this figure, but it took me a lot of time to build it, so I'm going to keep using it. So this is on the left over here. Imagine you're looking in somebody's ear, through the middle ear with the stapes removed, and the stapes would be here, but right now you're just seeing the outer layer of the temporal bone. And then over here is as if you've dug somebody's eye out, isn't that pleasant to think about, and chipped away the bone of the temporal bone, and now you can look at the cochlea from the front, and the person's ear would be here. So there's the first tube of your cochlea. It's a fluid-filled space embedded in a bony structure. If we cut away the bone just to see what this structure would look like in cross section. It would look like that. So it's kind of a round tube. There's another tube within that tube. So this green is the cochlear duct, which is filled with endolymph. The blue is perilymph. And you've got this top chamber is called the scala vestibuli. The bottom chamber is called the scala tympani. And this is the cochlea duct or cochlear duct, or sometimes called the scala media. Now, right here, it just looks like the whole thing is encased in bone, but there has to be some way for vibrations to get into this chamber and travel through it. So there are flexible, totally screwed up. Backtrack 1 second. If you look at this in the sagittal view, this is what it looks like. So you've actually got two chambers over here, the big one and the little one, but when you cut it in cross section, it looks like three chambers. Scala vestibuli, scala tympani, scala media, aka the cochlear duct. Now we add on the flexible membranes that allow vibrations to travel. So now here, looking at the bony structure of the middle ear, you can see where the oval window is. That's usually covered by the stapes, and then below that is the round window. So the oval window opens up onto, or I should say opposes, the perilymph in the scala vestibuli. And then the round window closes off the end of the scala tympani. So when the stapes pushes on the oval window, it sends a pressure wave through the fluid, and it goes around the end and comes back out this way and hits the round window, which then bows out a little bit. So you have two flexible membranes that allow for the vibrations to travel more efficiently through the fluid. Without the flexible round window down here, the vibrations from the oval window would be much more muffled because there wouldn't be as much flexibility. So this is what I just said. Pressure waves from the oval window are transmitted to the perilymph, and they travel through the cochlea to the round window. Don't worry about the helicotrema. It's not an important structure. I'm going to skip ahead a couple slides till I get to this slide right here. And I'll read off what it says and then go back and show you what I mean. So waves with frequencies that you don't hear below or above your threshold of hearing make their way to the round window without touching the basilar membrane. Sounds in your hearing range vibrate the basilar membrane. So if we go back, this membrane of your cochlear duct is called the basilar membrane. Those sounds that you hear have the ability to cause the basilar membrane to vibrate. So it is tuned to different frequencies, and it is able to vibrate when exposed to sounds that we can hear. Sounds that are above or below our frequency range of hearing still travel through the ear. They just don't cause deflections in the basilar membrane, so we don't detect them. I am going to stop there, and when we pick up in the next screencast, we'll go over the full structure of the cochlea and then how the structures within the cochlea transduce pressure waves in fluid into neurotransmitter release.